remember all the way back to Science 10 when we talked about the atom. And then we learned about like the billiard ball model and the raisin plum model and the Bohr model and the Rutherford model and the new up and coming model, the cloud model. Okay? If we go all the way back, dig deep in our recesses, Dalton is the very first one. He did the billiard ball model. And that was that there was a central piece to it and that there was just chunks of matter all around it. Okay? But as we get into our fancy TVs that we had in the 60s and 70s, where we had the cathode ray tube and not our super fancy ones that have LEDs in them now, once that came about, they had to change their thinking. And it came about like the billiard ball, and then it went to J.J. Thomson and the raisin plum model. It came about rather quickly, and everybody just built on each other. Okay? And a cathode ray tube is that tube that I showed you last week, where it has a set of parallel plates placed inside a glass tube. The glass tube is under low pressure. Sometimes it's under vacuum. And when a voltage is applied at the end down here, and it goes across the parallel plates, the gas inside the tube glows. Okay? And it emits from one of the electrodes to the other. So if you remember, there was two plates at either end of the tube. Okay, there was one here, there was one here. So J.J. Thomson, he's the not the billiard ball, he's the raisin plum theory guy. And so he did a lot of his work with cathode ray tubes. And he said that cathode rays travel in a straight line. They could be deflected by magnetic and electric fields. So hint, hint, we're going to be drawing on some of our Unit 2 knowledge. Okay. He said because they could be affected by electric and magnetic fields that they couldn't possibly be EMR energy. And that it didn't matter what the tube was made out of, whether it's the gas or the material of the electrodes, the emitted rays were the same. So then he came along and he applied an electric field using a second set of parallel plates. So here are his second set of parallel plates outside the tube. And what he noticed is that the beam of light, that's what he could see, excuse me, always bent towards the positive plate. And so then this is where he came up with the idea that there had to be tiny negatively charged particles inside of this model. Okay? And so lo and behold, we have the discovery of the electron. Now J.J. Thomson gets the credit, but he wasn't the only scientist at the time. Okay? So then he came up with the raisin plum model, and it's these little negative charged particles, just very much like raisins in a cinnamon bun, that they're all scattered about. Okay, and that this big piece was the positive ion. So now instead of just being these unknown chunks, now we have positive and we have negative. Right? So this is just jumping from Science 10 all the way into Physics 30. So then he continued to work with cathode ray tubes, and he learned about the charge to mass ratio of an electron. When he applied the magnetic field to the cathode ray, so the first thing he did was he applied an electric field, and he could bend that light towards the positive plate. Now he applies a magnet to that whole system, and he notices that they bend in a circular pattern. So now we're looking at radius, and we see this here. Magnetic force is equal to centripetal force. A magnetic force is found by what formula? Do we remember? How about Q, V, B? Not a capital V, sorry, that should be a small v for velocity. Okay, charge times velocity times B, which is magnetic field strength, measured in Teslas. Does that ring any bells from 2 units ago? No? Yeah? Some say yeah, some say no. Make that a small v. And how do we find centripetal force? Simplest way. Mass times centripetal acceleration. Now, do we remember what centripetal acceleration looks like? It's on your data sheets. Look how you solve for AC. V squared over R. So we have QBB is equal to mv squared over r. All we've done is we've just taken FC and FM and expanded them into their formulas. When we want to look at this charge to mass ratio, let's isolate Q and V on one side and put everything else on the other side. So we're going to have Q over M is going to be equal to V squared over R times B and V. Okay? And what can we say about that particular formula? How can we simplify it? V. One V will cancel out one of the squared V's. So charge to mass ratio is equal to velocity over your radius of your curvature times your magnetic field strength. Okay? This particular diagram here is explained using your third left-hand rule. Who remembers that piece? Is what? Your fingers is your direction of your magnetic field. Your electron movement is your thumb. Measure of direction of magnetic force is your palm. Okay? So that's how we can figure out what's going on. So let's jump right into it and let's look at some problems here. Charged particles are traveling horizontally at 3.6 times 10 to the 6 meters per second. When they enter a vertical magnetic field of 0.710 teslas, the radius of the arc is if the radius of the arc is deflected if the radius of the arc of the deflected particles is 9.5 times 10 to the negative 2 meters, what is the charge to mass ratio of the particles? So the easiest thing to do first is just to pull out the numbers and list what they are. Okay, so we have a horizontal velocity. Pen's gonna die. We have a magnetic field strength. And this is key here, where it says that the charged particles are traveling horizontal and then they enter a vertical magnetic field because magnetic field strength has to be perpendicular. If they were both traveling horizontal, then there would be no magnetic field strength. 0.710 teslas. And it says if the radius of the arc of the deflected particles is 9.50 times 10 to the negative 2 meters, what is the charge to mass ratio? Okay, we know that we get from centripetal force being equal to magnetic force, we get mv squared over r is equal to QVB, and we are looking for Q over M, and so we get V over RB. So Q over M would be equal to what? Anybody need a calculator? What are the units going to be, Daniel? Well, you got the kilograms piece. How do we measure charge? Coulombs. Coulombs per kilogram is going to be our units. Okay, you actually get 5.337. And when we're looking at significant digits, we only need 3 significant digits, so that 7 is going to round that 3 up to 5.34 times 10 to the 7th. Okay. Okay. Second question says, what is the speed of an electron that passes through an electrical field of 6.3 times 10 to the 3 newtons per coulomb and a magnetic field of 7.11 times 10 to the negative 3 teslas undeflected? Assume the magnetic field and electric field are perpendicular to each other. What does this undeflected tell us? Well, not so much force magnetic, but force net. Okay, so there's 0 newtons there. So what that means is that force magnetic is going to be equal to force centripetal. It's not going to be one minus the other. Oh, not force centripetal, force electric, sorry. Because it's passing through an electrical field and a magnetic field. So we know how to solve for force magnetic, QVB. And it tells us that because it says the magnetic and electric fields are perpendicular to each other. So that's key. We know that we can have this happen. How do we solve for force electric? There's several ways based on the information in the question. The first piece of information that we have is electric field strength, and it's 6.30 times 10 to the 3 newtons per coulomb. It's talking about an electron, and it has a magnetic field of 7.11 times 10 to the negative 3 teslas. So we know several things about an electron. What's one of them? Charge is. Okay, what's another thing that we know about an electron? Mass. And it is 10 to the negative 31 kilograms. So those are 2 things that we know because the question tells us we're dealing with an electron. Okay? So how do I solve for force electric Given the information that I have, look at your formula sheet. What would you choose? E is equal to FE over Q. So that means that FE is going to be equal to EQ. Okay? It's asking us to find the velocity. So I'm going to isolate V is equal to EQ over QB. And what do we see happening there? What's something we can do before we even plug in numbers? You can cancel Q out. Okay? So velocity is going to be equal to electric field strength over magnetic field strength. What do we get for our value? Does positive 5 make sense? Yes, because 3 minus negative 3 is 6. And so we would expect an answer somewhere around times 10 to the 6. So it must be 88.6 times 10 to the, or 0.886 times 10 to the 6, potentially. Okay, let's take, there's 5 questions. Let's take 20 minutes and we're going to work through these 5 questions. Okay, one of the experiments that was done to help um, solidify this theory is Rutherford's scattering experiment or Rutherford's gold foil experiment. There's multiple names, but it's this gold foil piece. So he took alpha particles, and alpha particles are 2 times the elementary charge. They directed it at a very thin piece of gold foil, and then, sorry, I got distracted by the message. And then what he noticed was that while most of the alpha particles, and an alpha particle is substantially larger than an electron. An electron is 9.11 times 10 to the negative 31 kilograms, and an alpha particle, I believe, is 6.65 times 10 to the negative 27 kilograms. So it's substantially larger than an electron. Most of those passed through the gold foil. However, some were scattered at different angles. Some actually even scattered right back on the line that they were shot in on. And so what happens is that he was able to look at this and determine that the mass of the atom, so remember he had the raisin plum model, he said that the mass of the atom isn't evenly distributed throughout the atom. So he said that the bulk of the positive piece, so Thomson, remember he said that there was just a bunch of negative pieces strewn about in his raisin plum model. Rutherford said, not quite. The positive ions are more towards the center of the mass or in a very small region of the atom, and that the bulk of it is actually electrons. And the electrons are small and they don't contribute a whole lot to the mass. Okay, so first we start with Dalton in Science 10, then we progress to J.J. Thomson in the Reason model, and then we progress into the Rutherford model. Rutherford models is the one where he could actually do an experiment and prove these pieces out. However, there are some flaws, as usual, in Rutherford's model. If the nucleus of the atom is positive and it's concentrated at the center of the atom, what keeps the electrons from being drawn into that center and having the atom collapse in on itself? So then we move into Bohr's model and we get this orbiting diagram, orbiting like the planets around the sun. Okay, so we have an accelerating charged particle, so we're still expanding on the model before us. We have an accelerating charged particle that will emit. So remember, in Thomson's model, he said it's not EMR. Now we're going to the Rutherford model and beyond, and we're saying, wait a minute, EMR is a part of it. And if the electron is emitting energy, it will lose kinetic energy and spiral into the nucleus, which would collapse the atom. Okay? So this is kind of the diagram that we show you in school. This is the Bohr model. And so where we circle around the nucleus, electrons orbit around the nucleus. As we move into atomic physics and the end of EMR and we take on this wave-particle duality theory, we now know, or we now suspect, that we still have a kind of core positive, and out here we have this dusting of electrons, this cloud. So they don't necessarily orbit in a specific path like we think of around the sun. Mercury orbits in a specific pattern. Venus, Earth, Mars, Jupiter, they all orbit in a specific pattern around the sun. We know that that's not the particular case with electrons around a proton-dense nucleus, but they kind of exist in a cloud around the nucleus. Okay? But this model here is still the traditional model as being taught because they don't have enough knowledge or proof of theories to go 100% into the cloud model. So this is where we stop. We stop at this level of knowledge. So let's look at practice problems 8 to 9 on page 288. And it says, briefly describe the planetary model of the atom. Well, the planetary model of the atom is which one? The one with which, Avery? I just didn't hear you. Right, where the electrons are orbiting in a path very much similar to the planetary system. Okay. Why does the scattering angle increase as alpha particles pass closer to the nucleus?